In this section, we're going to take a look at probability distributions. So when we're talking about probability distributions, we're now taking a look, instead of just the probability of getting one tail when you flip a coin 3 times, we're looking at, if we flip a coin 3 times, how many times do we get no tails, and 1 tail, and 2 tails, and 3 tails, and looking at them as separate situations. So we look at all those different probabilities, and we look at them often in a table or graphically. So when we're looking at the probabilities, we're comparing this concept of our random variable. So that's the thing we're looking for. It can have a range of values. We use our random variable. X denotes when we're talking about the whole situation, all those different probabilities, the capital X. And then when we use a lowercase x, we're looking at any individual probability. So when we're using the capital X, we're talking about the collective whole of all the different number of tails we could flip from my example. And with the lowercase x, we're looking at the number of times we could flip tails twice, or any other specific one. In terms of our sample spaces, we have a couple different types of sample spaces we could look at. We could have discrete values, which are those numbers such as 1, 2, 3, 4. They have to be exact values. There's no values in between these, so you can't have a result of 1.2. So if we were looking at flipping the coin, how many times directly does that happen? It happens, okay, we have either, you can't have 1.5 tails. You got to have 1 tail, or you have 2 tails very distinctly. In the term continuous, when we're looking at continuous values, these are within ranges. So we might say, look at the heights of students in the class, and we could have a range between 140 inches or 140 centimeters and 150 centimeters, and then a range between 151 centimeters and 160 centimeters. So we could fit within that range of numbers. So we're looking in between those numbers and in between. When we're looking at these visually, we can use what's called probability histograms. And so here I have a probability histogram example. So the histogram illustrates the probability distributions with equal intervals on the x horizontal axis and probabilities on the y-axis. So we'll always have our probability going on this vertical y-axis here, and then our horizontal axis will be those intervals that we're using, either the discrete or continuous intervals. So here I have a discrete situation with the probability of throwing a basketball or into a hoop on a free throw. So how many tries does it take to get it in? So 5% of the time, this person gets it in once. 15% of the time in 2 throws. 25% of the time it takes 3 or 4 throws each. And then 20% of the time it takes 5 throws, and then 10% of the time it'll take a total of 6 throws to get in. So we're just looking at how many throws does it take before it goes in the first time, and what's the probability. And that could be a possible probability distribution. Moving on, if we want to actually get to some work with this, what we're going to do is create a probability distribution for flipping a coin 5 times, and from that we're going to construct a table. So if we're flipping a coin 5 times, what's the probability distribution of flipping tails? So and when I'm flipping a coin 5 times, I could flip it and get 5 heads in a row. With no tails, I could possibly get 1 tail. I could get 2 tails, 3 tails in all those flips, 4 tails in all those flips, or I could get 5 tails in all those flips. So this row here is accounting for the times that I do not get any tails. And the frequency of that happening, there's only one case where you're not going to get any tails. That's when you get the case of all heads. Mathematically, we could use our 5, choose 5 choose 0, and that would equal 1. So we can calculate that out using our 5 choose 0. 5 choose 1 if we're getting one tail. So which of those 5 flips is going to be the one tail? So that's going to be 5. You could have 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5 as all our different cases, to cover all our cases. So this will give us our theoretical frequency. So you could, if you were to get it twice, there are 10 ways to do that. There's 10 ways of getting it thrice. And then there are 5 ways of getting it 4 times and 1 way of flipping it. All 5 are heads. Now that is a total of 32. 2 to the power of 5 would be the total number of outcomes that we're looking at. So the probability in each case, the probability of flipping it once is 1 out of 32. Probability of flipping it no times is 1 out of 32. Once is 5 out of 32. It's 10 out of 32 to flip it twice. It's 10 out of 32 to flip it 3 times. It's 5 out of 32 to flip it 4 times, and 1 out of 32 to flip it all 5 times. I'm going to leave it with the same, or not simplified. So we could simplify 10 out of 32 to 5 out of 16, but we're going to leave it, and you'll see why shortly here when we get to the next step. So next we're going to look at, so what we have here is just, this is a probability distribution. We could then actually graph this. We could make a graph, and I'll just do a quick little sketch here. And we could graph the probability versus the number of tails. And then we'd work these out into our percentages. Do note that if you add all those probabilities up, they do add up to 100 or 1, right? 1 out of 32, 1 plus 5 plus 10 plus 10 plus 5 plus 1 is going to give you a total of 32. So we have, just looking at all my probabilities here, okay, so the highest we would go is 30. I'm going to put 32 on there. It's 31.25 for the 10s. But we'd have our 1 flip, or 0, 1, 2, 3, 4, and 5 tails. And so our 2 and 3 go all the way up to just about 32. Okay, so this is just a really rough, quick sketch, but they would be way up there. The probability of flipping it once, 5 out of 32, is going to give us about halfway. So if that's 32, we'll say that's 30. That's about 15-ish, somewhere around here. So that would be about here, 15% of the time. And then 0 and 5 are all the way down at a lowly old 3% of the time, so maybe down here, something like that. So that would be like a quick little sketch of that probability distribution. You can convert those to decimal and then graph out that, or percentages, and graph that out like that. So it's kind of like a bar graph in that you're putting the frequency of those occurrences in terms of their probability percentage. So now the next thing we can look at that's useful when we're talking about these probability distributions is the weighted mean. And so the mean, we'll often use, again, the word average for mean, but the mean is when you add all the numbers up and divide by the number of items you added up. The weighted mean is the mean of a set of numbers, but each number is multiplied by its weight or frequency. So how often it occurs, or if there's a value to it, to that, and we'll look at some examples of that one later. And then we divide it by their sum by the total weight. So if we wanted to calculate the weighted mean of our flips here, well, we have 0 tails, and we multiply it by 1, okay, because it occurs 1 time. That's the frequency or weight. So 0 is weighted with 1, plus 1 is weighted with 5, plus 2 is weighted with 10, plus 3, which is weighted with 10, plus 4, which is weighted with 5, plus 5, which is weighted with 1. So those are all the numbers. Normally, if we were doing an average, we might take all the frequencies here, we might add all those up, right? So we'd add up 1 and 5 and 30, all the way up to 32 and find the average of those. But in this case, we have to find the weight of those. So we take the weight of the occurrence and the frequency that it happened, and we multiply those together. So we're going to do that, and that is a times there. And then all that big long mess is going to be over the total frequencies, which is 32. So we take our values, 0, 1, 2, 3, 4, and 5 here, our x values, and we multiply them by their frequency in this case. And those are the 1, 5, 10, 10, 5, and 1. And then we're going to divide that by 32. When we do that, we end up with a weighted mean of 2.5. So our weighted mean in this case is 2.5. And this here would be the typical number of tails in 5 flips. So typically we would expect to find 2.5 tails in 5 flips. Does that mean there's 2.5 tails? No, you can't have 2.5. So ideally in our case it's going to be 2 or 3. But typically you can say there's going to be 2.5 tails. And that would give an idea of how this frequency is working out. Moving on, we have, similar to the weighted mean, is the expected value. And so this is the value that we would expect to get on average with these. So the expected value is the predicted average of all possible outcomes. We use it by finding the sum of each outcome times its probability. So what I mean by that is we're going to take each of our outcomes, x, and we're going to multiply the probability of x. So this is the table from before. I left them all in 32s so that we can easily add them without having to get a common denominator. This is the general equation for this. The expected value of capital X of flipping the coin and getting tails is I equals 1. Okay, this is just our starting value. This is the sum notation to n. In our case, n would be 5 of x times px. So this is just a way to write the sum of these numbers. Okay, it's a mathematical notation, and that weird looking e there is it's the way of writing the sum of whatever comes next between these two values. So that's just a mathematical notation that we work with. So let's actually calculate the sum of the values of these 5 flips. So we have 0 times 1 over 32. That's just going to be 0. We have 1 times 5 over 32, which is going to be 5 over 32. 2 times 10 over 32, which is going to give us 20 over 32. And then 3 times 10 over 32, which is going to give us 30 over 32. 4 times 5 over 32 is going to give us 20 over 32. And 5 times 1 over 32 is going to give us 5 over 32. There's all our numbers. There's all our multiples. So now we need to sum those up. And again, we left them over 32 because we want to not have to find a common denominator. So 5 plus 20 plus 30 plus 20 plus 5, that's going to give us 50, 60, 80 out of 32. And then 80 out of 32 would simplify down to 2.5. So here our expected value is also 2.5. So we would expect that in any case, on average, 5 flips of a coin would result in 2.5 tails. And using this notation up here, the expected value of our situation, x just represents our situation here, is the sum from item 0, first x is 0, all the way up to 5 in this case, of x times probability of x. So x would go 0, 1, 2, 3, 4, 5. And so it's 0 times the probability of 0 tails. 1 times the probability of 1 tail. 2 times the probability of 2 tails. And this just means you're adding them all up, is what it means there. It's just a short notation for adding. So when we're flipping these coins, we're looking at that 2.5 as our expected value. Now, similar type of question here. We have a lottery that has a $1 million grand prize, 3 $5,000 prize or $500,000 prizes, and 10 $10,000 prizes. Tickets are $5 each, and 3 million were sold. There was a spelling mistake there. Notice the correction. What is the expected value of a ticket? So here we can calculate our expected value of a ticket, meaning what do we expect to get out of it? And we can do that by one of two ways. One way, our expected value is the sum of each value times its probability minus the value of the ticket itself you would purchase. So one way is take our expected value and we'll sum up. We have $1 million times the probability of getting $1 million, which is 1 in 3 million. Plus, so that's our x, that's our p, probability of x. And then the next one would be 500,000 times, and now we have 3 $500,000 prizes over 3 million. Plus, and we're continuing it down here because I'm running out of room. And you can see this gets pretty long. $10,000 prize. And we have 10 of those. So times 10 out of 3 million. And then that covers all our prizes. And then we would subtract the value of a ticket. Okay, so this will tell us what we would win minus how much we spent. Okay, so this first part here, this is your winning, how much you would expect to win minus how much you paid for a ticket. So your expectation here, when you work that all out, you end up getting negative 4.13. So you would expect that you would lose $4.13 on any ticket. If you were to buy a ticket, you're expecting that you're going to lose $4.13. If we look at this the other way, the expected value, which will give us the same answer, but the expected value is the total value of all the prizes divided by the number of tickets minus the price of each ticket. And so in that case, we would do get our total value of all the prizes. What we do in that case is have, and you'll notice it's very similar here, 1 million times 1 plus 500,000 times 3 plus 10,000 times 10. All of that divided by the 3 million minus a 5. You're going to get the same answer. So that's another way of doing it. If you want a full example, because I've ran out of room here and this has been a 21-minute video, take a look at the example 3 in the textbook for section 4.1. So there we have probability distributions. So again, we are looking at creating histograms of probability where we have our outcomes versus our probability. We can make distribution tables where we take all our outcomes, find their frequency, and then the probability of each of those occurring. We can calculate weighted mean by taking each outcome and multiplying it by its frequency and adding those all up and then dividing by the total number of occurrences or total frequencies. We have expected value, which is our predicted average, and we do that by summing up each outcome multiplied by its probability, and then we sum, so that's the sum of all those. And then in cases where we have actual values assigned to each thing, we can multiply those values by their probability again and tally those up. If you're purchasing tickets, we would take away any cost associated, and that would be the expected winnings. Everybody could expect to lose so for every ticket sold, everybody would expect to lose $4.13. All right, that's a long one, but there's some bigger content in there. So make sure you ask questions if you're not sure about anything.